All right, welcome back. Make sure you guys sign in before we start. So go down to the description, click on that link. It says sign in, and then sign in, and it helps me out. You know, gets me, helps my boss know that my work is being seen, I guess. Okay, so let's get into it. So number one, this week we went over circular motion and gravity. Fun stuff. Okay, so number one. A car makes a circular turn of radius 20 meters. The coefficient of static friction between the tires and the road is 0.60. What is the maximum speed at which the car can safely travel? What is the maximum speed at which the car safely makes the turn without sliding? Okay. So what is the maximum speed at which the car can safely make the turn without sliding? Okay, so let's kind of draw our car. What is going on with our car? Our car, and it's going around a turn. Okay, car is going around the turn. The friction between the tires and the road, right? So it's keeping us on the road, the friction, right? Friction is keeping us on the road. Yeah, static friction. Okay, so essentially we want to know the maximum speed at which the car safely makes the turn without sliding. Okay, so what we have to do here is it doesn't give us the mass of this car. So what I'm going to do is I'm going to set the force of friction, force of static friction, equal to the force, the centripetal force of the car going around this current turn. Okay. So we know these two equations. We know the force of friction is mu s times the normal force equals, and then the centripetal force is mass times velocity squared all over the radius, right? So, and then the radius, so is the center, right? So then from here to the car is like 20 meters, okay? Okay, and then we know that the normal force is just mass times gravity, right? So mu s times mass times gravity equals mass velocity squared over r. Okay, so then we don't have the mass, but what we can do is sort of cancel these two variables out. So now it doesn't matter, right? We don't need the mass to solve this problem. So now what we got is ms times g equals velocity squared over r. And we have all those variables, right? So we have 0.60 times 9.8 equals velocity squared, what we want to find, right? The maximum velocity over 20, right? So essentially what this is telling us here is if we were to increase, or let's get the velocity first, and then we'll go through that. So what is the velocity here? When we solve it out, is 10.84 meters per second. Okay, so essentially what this is doing here is if we were to increase this velocity at all, right? If it went to 11 meters per second, our car would no longer stay in that circular motion on the track because the friction, the force given by like the centripetal force is going to overcome the frictional force that the tires have on the road, right? The static friction. So now the car is just going to slide off the road. That's what's going on there. So that's the maximum speed that we can have is 10.84. All right, so number two, a 1,000 kilogram car travels on a road at a speed of 20 meters per second. All right, so we got our car right here. This is the car, if you guys didn't notice. And calculate the normal force exerted by the road at point A. All right, so this guy right here, and point B, that right there. The radius of the curvature is 100 meters. What is the maximum speed that the car could travel at point B without losing contact with the road, right? So two questions. First question, part A, calculate the normal force exerted by the road at point A and B. Okay, So let's think about it. Let us think about it. So when the car is right here, I'm just going to draw a box. Car is right here. We have the force of gravity, right? Force of gravity acting on this guy. And then we have that opposing normal force, okay, whatever that is. That normal force, in this case, is going to be a combination of the force due to gravity and the centripetal force, right? So the centripetal force is pushing this car upwards, right? It's pushing this car upwards to stay in that circular motion, right? So then if we do this at point A, so part A, right? Then to calculate this, right, the force, the normal force, is going to be the force due to gravity, which is mass times gravity, plus the centripetal force, which is, let's do this right now. Okay, so essentially what's going on here is you can think of this as like you're standing on a scale down there, right? And if you're just at rest on the scale down there at part A, then the normal force would just be the force due to gravity, right? So, you know, whatever your weight would be, in this case, the car would be 1,000 kilograms, right? It's not moving, no other forces are acting on it. But because it's in motion and we have that centripetal force that is also pushing the car up, it's going to add, the road is going to need more normal force to keep the car in that circular motion, right? So that's why we add the centripetal force that's going on, right? So I want to calculate it. For normal force equals 1,000 times 9.8, and then we know the centripetal force is it's the whole mass times velocity squared over radius, right? So the mass is 1,000 kilograms, velocity is 20 meters per second squared over 100, right? That's the radius, right? Yeah. So when we calculate it, the normal force here is 13,800 newtons. Okay. Cool. So let's go to part B. What do you guys think we're going to do for part B? I'm going to draw our car just as a box. So now our normal force is still going up, right? Force normal going up, gravity, force due to gravity is going down. But now our centripetal force is going down, right? So essentially what's happening is our car is going to be a lot lighter here, right? So we're going to take our, actually, I'll do this again. So this is supposed to be part B. We're going to take our normal force, and that is going to be, we're going to take the force due to gravity, which is mass times gravity, and now we're going to subtract the centripetal force, right? We're going to subtract centripetal force, okay? Because our car is going to be lighter now because it's going on top of the hill, right? It's no longer being pushed against the hill. It's actually like, you know, almost levitating across the hill. It's going fast enough. So when we calculate it, we got 1,009.8 minus same deal, right? It's going same speed, same radius. So now our force, normal force is 5,800 newtons. Cool. Right, and it makes sense, right? Our normal force at part B, at point B, is a lot lower than at point 1 because at point 1, we are adding that centripetal force into it, right? Yeah, the ground is pushing into the car with a greater force than it is at point B, essentially is what is going on. Okay, part B. So part B, I'll do a different color, make sure. What is part B? So part B is what is the maximum speed that the car can travel at point B without losing contact with the road. Okay, so what does that mean? Well, that means that now, what is the maximum speed? So that means that the force that the hill is exerting on the car, right, that normal force, is now going to be 0, right? Because we're our car, that is the point where our car is going to lose contact, right? So our normal force is equal to 0 now, okay? So now if we keep that same equation that we made for point B, so the normal force equals mass times gravity minus that, and we know that the normal force equals 0, then we can just solve, right? So then we bring, let's bring the centripetal force to the other side, right here. 0 equals mg there, and then when we solve, boom. Okay, so now we do know. Okay, so now we could just solve and find the maximum velocity. All right, we know the FC centripetal force equation. So mass velocity squared r equals mass times gravity. Masses cancel out, but we have a mass, so it doesn't really matter. But anyways, velocity squared over 100 equals gravity, which is 9.8, right? Okay, when you solve velocity equals 31.305 meters per second. So that is the maximum speed that this car can go without losing contact with the road, right? And when the normal force is equal to 0, that is that point in which the car is about to lose contact with the road, right? That is what's going on here. All right, number 3, if you stood on a planet having a mass that is 4 times more than the Earth's mass with the same radius, how much more would you weigh? Okay, let's think about this. So we have this equation, right? Force equals gravity constant, mass 1, mass 2, all over r squared, right? So that is essentially, let's say mass 1 is the Earth, right? So mass 1 is the Earth, mass 2 is you, right? Or mass 1 was the planet in this case, right? So if we were to increase mass 1 by 4, right? So now we have F equals G. Now it's 4 times M, and then just regular M over R squared. Now it's pretty easy to see that we just increased our force, right? We increased our force by 4, right? By a factor of 4, right? Because if we increase this mass up here, right, let me circle it. Increase this mass right there by 4, then that is the same as increasing this this force right here by 4, by a factor of 4. Okay, so you could think of this like, imagine you're stepping on a scale, right? And your mass stays the same, right? So if you weigh, or if your mass is 100 kilograms on Earth, your mass is still going to be 100 kilograms on this new planet, but your weight is going to be different, right? Because your weight factors in gravity. So what's going on here is essentially your gravity, the gravitational pull of this new planet is much stronger than Earth's gravitational pull because it's larger, right? So the bigger the mass is, the larger the pull is on the object, right? And you can kind of think of like, oh, the sun's really huge, all the planets go around the sun, right? So if we increase the force of gravity by 4, then your weight is going to increase by a factor of 4, right? So our weight increases by a factor of 4. Cool, that's the answer right there. Okay, so if an astronaut were exactly halfway between Earth and the Moon, the net gravitational force exerted on the astronaut by these two objects would be either directed towards the Moon, 0, or directed towards the Earth. Okay. So just thinking about this like logically, if we know that the bigger mass is going to have the stronger gravitational pull, what are we going to think? Well, Earth is much bigger than the Moon, so it's going to have a larger gravitational pull on this astronaut. So automatically I can just think about it, and I know that the net force is going to be directed towards Earth, right? But let's do it. Let's show you via math, right? So is that one. Okay, so this is for Earth, this equation. All right, so we got force equals G, or this is just a standard equation, right? So this is the equation I showed you last question. And then this is moon over here, okay? Same equation, G M R squared, right? So for the Earth is actually the mass of the Earth. So let's say mass 1 is Earth, mass 2 on both these is going to be just the astronaut, right? Mass 1 here, so that's the Earth. That is the mass of the moon in this case, okay? Arrows help, okay. So it just so happens that the Earth is 81 times the mass of the moon, right? Equals G, 81, that's 1, that's 2. So if we increase the mass by 81 times, that just means our gravitational pull, right, is going to increase by 81 times. So F is increasing by 81 times, 81 times, by a factor of 81. So the net force is going to be directed towards Earth, right? In this case. All right, last one. So what is the speed of the satellite moving in a circular orbit at a height of that above the surface of the Earth? Radius of the Earth is that, mass of the Earth is that. Okay, so let's draw it out. We got our Earth, okay, and we have our satellite out here. So satellite, Earth, okay. Our satellite is orbiting around our Earth, all right? And we want to know the speed at which it is orbiting around our Earth. We're given the mass of the Earth. We're given the radius of the Earth. We're given, okay, so we're given the height. So essentially the distance between the satellite and the Earth is 3.8 times 10 to the 6. And then we know the radius of the Earth, right? So one thing that you have to understand is we go from center to center, all right? So the center of the Earth to the center of the satellite. So I guess we can just assume that this radius right here is going to the center of the satellite, or that the satellite's so small it doesn't, really matter too much. Yeah, let's do it. So we got essentially a couple forces going on here. We got the Earth's gravitational pull, right? So the Earth is pulling in the satellite. Oh, someone just called. Okay, anyways. This is my sister's iPad, so sorry about that. The Earth is pulling the satellite towards it, and then we have the centripetal force, right? That's keeping it also in orbit. So essentially, what speed is the satellite moving in a circular orbit? If we make the force due to gravity equal to the centripetal force, right? And then we put in our equation. So G M R squared equals mv squared over R. Now, this sort of takes care of our problem, right, with the mass, because let's say the big M is the mass of the Earth. And we know that small m is going to be the mass of the satellite. Well, now the masses of the satellite cancel out, right? When we solve for it, when we solve for like velocity, we're going to get velocity equals square root of g times mass of the Earth over r. Okay, so now if we just plug in our variables, we can get it. So understand now that r is not just 3.8 times 10 to the power 6 meters. It is 3.8 times 10 to the power 6 plus the radius, or the Earth right here, right? So you have to do from center to center. So this is 6.38 times 10 to the power 6 meters. Okay, so now when we do all this, velocity equals G is I'm using 6.67 times 10 negative 11, 5.97 times 10 is 24 over. So yeah, G is just a constant. It's always going to be that number. 6 point. Okay, so what this is now for R, I'm just adding 3.6 or 3.8 times 10 to the power 6 plus 6.38 times 10 to the power 6. I'm adding those two together, and that'll be my R variable. 8 times 10 to the power 6. Okay, when I solve, I'll get a velocity of 6,254.3 meters per second. Okay, so yeah, if you have any questions, feel free to comment on this video or come to my office hours this week or any other week, and I'll help you out the best of my ability. All right, keep studying. See you later.